Well, class, we are going to now move into sections 3 and 4 of chapter 16, and that's going to get us into the autoionization of water as well as pH and what pH is. So let's go ahead and get into it. So water, like we said previously, is amphiprotic, meaning it could be a acid or a base. But if you have pure water, you're always going to have a few molecules that act as a base and a few that act as an acid. And so you have what is called, so this is called autoionization, where so you have pure water, some of that water is not going to remain as H2O, and some of it's going to donate a proton, and others are going to gain a proton. And so you get some H3O pluses present, and you also get OH minuses present. So what this gives us is we can write an equilibrium expression for this process. And you notice how water, like H2O, is not a reactant. It's not in this equilibrium expression because we omit water in concentrations because it's the solvent. It's not actually it's not a dissolvable thing in there. So we get this Kc equals the concentration of H3O plus times the concentration of OH minus. Well, water has its own special equilibrium constant, referred to as the ion product constant, and it's written as Kw. And at 25 degrees Celsius, it's 1 times 10 to the negative 14th. And that value, we're going to be utilizing that Kw a number of different ways in the next couple of slides. So this leads us or moves us towards pH. Now, pH is the negative base 10 logarithm of the concentration of the hydronium ion, or this equation. pH equals the negative log of the concentration of the H3O plus. And log is base 10, so that's that little component there and there. So, in pure water, Kw is equal to the concentration of H3O plus times the concentration of OH minus, and the value at 25 degrees Celsius is 1 times 10 to the negative 14th. So if pure water is going to have an equal amount of both the hydronium ion and the hydroxide ion, you do some different math because it'd be double. So basically the concentration, if you take the square root of 1 times 10 to the negative 14th, when things are neutral, okay, so when you have just pure water, the concentration of H3O plus will be 1 times 10 to the negative 7th. It would also be the same for the OH minus. So this means, pure water, when you take the negative log of the concentration of H3O plus, which is 1 times 10 to the negative 7th for pure water, then you get a pH of 7. Okay, so pure water, pH is 7. It has equal amounts of H3O plus and OH minus. And so you've got this range down here at the bottom of this slide. So acids or anything that have a concentration of H3O plus greater than 1 times 10 to the negative 7th, and your OH minuses are less than 1 times 10 to the negative 7th, and you have pH values that are less than 7. Neutral, you're at 7, and bases or anything greater of OH minus concentrations, a pH greater than 7. And I'm now probably going to hit slides that just repeat what I just said. So an acid has a higher H3O plus concentration than pure water, and its pH is less than 7. A base has a lower H3O plus concentration than pure water, so its pH is greater than 7. So here you have some common items that you might come across, and they have their relative hydronium ion concentrations and relative pHs associated with it. And there's some interesting things like looking at tomatoes versus bananas, or stomach acid, cola, and then going down like bleach and ammonia, borax, different things you might come across, tears and blood. So all just kind of interesting anecdotes. All right, so the other P scale. Okay, the P is in pH tells us to take the negative base 10 logarithm of the quantity. So for pH, we're taking the negative base 10 log of the hydronium ion. But we can do the same thing for other substances. So we can take the negative base 10 log of the OH minus concentration, and this would give us what we call the POH. Or we can take the negative log of the KW and get the PKW. Okay, so we can do this because with the relationship that the concentration of H3O plus times concentration of OH minus is equal to KW, we can, if we took the negative log of all of these, okay, of all of these values kind of separately, okay, so the negative log of the KW would give us 14, okay, and then you have this relationship, negative log of the concentration of H3O plus the negative log of OH minus. Well, we could rewrite these as being pH plus POH equals PKW, or 14. So let's say you know the pH is 4. Then you can find the POH by subtracting 4 from 14 and getting the POH. Now, what are the ways that we measure pH? And we did this in the lab on Tuesday. We use different indicators typically to determine the pH. And different indicators have different colors and transitions depending on the substance you're working with. So here we have, in the past you've probably worked with litmus paper where like red litmus paper turns blue when the pH is equal to 8 or higher, and blue litmus paper turns red when the pH is lower, about 5 or lower. So, but we are going to be doing actually a lab where you have to determine the correct indicator. I think that's the 3rd week of acid-base labs. But indicators are really great in that sense where you're looking for that subtle difference. You guys worked with phenolphthalein, so you can see right there that its range is between 8 and 10 when you start seeing a color change. So, but depending on what you're titrating, you might choose a different indicator to see a change and a temperature. Now, another way that we can also measure pH is using pH meters, which we also used in the lab on Tuesday, and it's often more accurate as long as the pH meters are calibrated. It's usually a pretty accurate way of measuring pH. So that's it for today. Please prepare a little bit. I'm going to have a kind of a little quiz question for you tomorrow in class related to equilibrium and chapter 15. So maybe kind of review some of your notes, and I will probably pop in and say hey, and have a great weekend.